try to record the screens like I did last quarter as well. And so we'll begin. Okay, so this is computational statistics and optimization, or I guess computation and optimization for statistics. Let's see. And if I pull up kind of our syllabus, it covers these different topics: matrix algebra, principal component analysis, differentiation and optimization, and the EM and MM algorithms. And these are all they're very important topics for computation and optimization for statistics. However, I was trying to look for maybe a textbook that I could refer you guys to, and in my search, I couldn't find any one textbook that kind of covered all of these topics. And so these are like four different, like you can get a textbook on matrix algebra, specifically with a statistics perspective. You can get a textbook on principal component analysis, or just kind of, which is a subtopic in multivariate statistics. There's many textbooks on multivariate statistics, of which principal component analysis will probably be a significant portion of it. And then there are textbooks on, optimization, differentiation and optimization, and maybe the EM and MM algorithms will be included in a textbook on optimization. And so we'll be kind of exploring each of these topics, one by one as we go through, and we'll have a homework assignment and a test. And so we're going to get started with kind of this stuff on matrix algebra. We'll begin with vectors and vector spaces. Okay, so in our first topic of matrix algebra, and specifically we will begin with vectors and vector spaces. And I'll save these and post these slides online as well. And today is January 6th. Look at that. 2016. We're going to have it's a leap year. There's the Olympics. I don't know. Presidential election. It's exciting times. What a time to be alive. Okay. I guess that was funny. All right. Thank you for laughing. My student reviews came back, and for the most part they were positive. Although one review kind of hurt my feelings. It said, "Don't make jokes. You're not funny." That's just mean. Okay. Good thing I already turned in your grades. All right. Okay. Okay. So vectors and vector spaces for a positive integer n. Okay. We have an n vector. Is going to be defined as x equal to x1, x2, dot, 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 up to x sub n, okay? Or can, written as horizontally, x1, x2, okay? And we would, we say x sub I for I equal to 1 through n are the elements. Okay, and we say n is the order of the vector. Okay, and so, if we're talking about n2, like two-dimensional space, then you just kind of have this Cartesian coordinate plane system, okay? And so we have the this is the set of n vectors with real elements, the real space, real n. Okay, this is and so we can define this this as the set of all n vectors okay, where every x sub I is an element of the real numbers, okay, for all. So this, for all i's 1 through n. Okay, this is just the other way of writing this. Okay, and just kind of to think of what an n vector is, okay, so we can think of an n vector as the same thing as a point in n-dimensional space. Okay, and so, this just kind of formalizes a lot of stuff, but if you just think of, I've got a spot 2, 2, this is a vector in 2 space, and it's just a single point, right? Or, we can illustrate it as kind of this a vector, but it's really just that, defining that point right there, okay? And it's hard for me to draw anything with more than 2 dimensions on the board here. Okay. I'm going to just try to gauge when I can flip to the next slide. I feel like I can. So, okay. We can talk about. So I guess this will be our next subsection here. Operations on vectors. Okay, and so we have our basic operations like addition. Okay, and so if we say let x be an n vector, and y be another n vector, then we can define z as x plus y, which we will define as exactly as we would expect, kind of element-wise addition. x1 plus y1, x2 plus y2, so on and so forth, all the way up to xn plus yn. Okay, and this gives rise to the zero vector. Okay, and so. We will say that 0n, this is going to be defined as 0 all the way up to 0n. There's n elements of zeros. And this has the property where x plus the zero vector is equal to x, and so is the additive identity. So adding the zero vector leaves you with the original vector, which is not surprising. I think this is rather straightforward, but I don't know. I guess it's good to define these things here. Okay, you can add a scalar, addition of a scalar. And that is, so we will say if some element C comes from, the set of real numbers, okay, and then so we will say, we will define x plus c as adding the element c to each element of x. So x1 plus c, x2 plus c. Okay. So this is an n vector still. Okay, and then we have scalar multiplication. And okay, and so same thing. We still have we're going to let x equal this thing, and we will say if we say y is equal to c times x, this is going to be each element of x, c times x1, c times x2, all the way up to c times xn. Okay? So I think this is stuff we're all familiar with, I hope. And we can also talk about different vectors being linearly independent. Okay, so let's see. Maybe this is worthy of its own. I'll flip to the next slide here. Okay, so maybe we have a set of vectors. V1, V2, up through Vk. Okay, and we say this set is linearly independent if we can create a set of, I guess if the only way, here I'm gonna write this down. Okay. So if these add up to the zero vector, the only way this can happen if they're linearly independent is when all of the elements A through AK are zero. Okay, if this being true means that A1, A2, up through AK are all equal 0. Okay? So basically, just this means that, so again, these are scalars over here. This means that, you know, we cannot make any of the vectors v1 through vk from a combination of the other vectors. Okay, so, you know, the only way we can get the vectors to kind of add up and cancel each other out is by forcing all of the scalars in front of them to be 0. Okay, and that means our set of vectors would be linearly independent. Okay. Is that all right? All right, we can talk about subspaces. Okay, so we've got a subspace is a subset of a vector space V that itself is a vector space is called a subspace. Okay. All right. So so here's an example. So we can have the three-dimensional real space of x1, x2, x3, where these are coming from real number space is a vector space. Okay, and then we can have a basis B, which is going to be these three particular vectors, okay? 1, 0, 0, 0, 1, 0. Okay, and we can call this E1, E2, and E3, and this would count as a subspace of this vector space. Okay, so this okay, and so any x that's an element of the three-dimensional real space can be written as a combination of these three basis vectors. Okay. Okay, and so you know, if x is equal, I mean, this is kind of trivial, but you know, if we say x is x1, x2, x3, you know, it's pretty easy to see that that this can be written as the scalar x1 times 1, 0, 0 plus x2 times 0, 1, 0 plus x3. Okay. Or x1 e1 plus okay. You know, a further, you know, we can also say that a subspace. I'm sorry. This is not a subspace of 3. This is kind of. I'm sorry. This is just a basis. I apologize. Of the real space. So you know, a subspace of the three-dimensional real space could be the two-dimensional real space. So, you know, you could pick any kind of plane within that three-dimensional space, and that also forms a vector space as well. Okay, so any two-dimensional plane in the three-dimensional space is a subspace, okay, of the 3D space. Okay. All right. We'll go on there. Okay. Other operations we can talk about. Inner products. Inner products of vectors. Okay, so we'll just start off with we'll let x1 equal our and y. No, just not x1. This is x, and y is our vectors, our n vectors, y of x and n. Okay. Okay, and so the inner product of x and y, which we can write that way, we can define as the sum of each element xi times yi for all elements from 1 to n. Okay, or this is the same as can be thought of as our dot product. Okay, or if we were to transpose the x. Okay, so this can also be the dot product of x and y. So it's element-wise multiplication and then adding them all together. Okay. Multiplication and summation. Okay, so let's say, so we'll have, so here's some properties of dot products. Dot products or inner products. So if we got x, y, z, and 0 as elements of our vector space V, okay. So the dot product of x and x will always be greater than or equal to 0. Okay, this is kind of like the analog for scalars would be just like when you square a number, it's always positive. Okay, kind of like that, and you know. And if the inner product is equal to 0, then x is the 0 vector there, okay? The inner product of x and y is the same as the inner product of y and x. The inner product of ax and y is the same as a times the inner product of x and y. Okay, for all a that's coming from the real number set. And if we were to add x and y together and do an inner product of z, there's kind of like this It's the same as x inner product z. It's like this distributive property. This is exciting stuff, guys. Okay, yeah, I know. So, we're starting off with a bunch of matrix algebra stuff. And so, our first homework assignment is going to have a lot of this vector and norm and this stuff. So we just got to get used to it, and then we'll apply it to like some data sets, and we'll see like, oh, this is just a simple application. But right now we're just seeing a whole bunch of letters, and it's already 2:40. My goodness. Okay. Well, thanks for hanging in there. All right, so we got the Cauchy-Schwarz inequality. All right. This is so. Let's see. Let me just flip through my notes here. Okay. Yeah, we don't have this yet. The dot product, there's this geometric interpretation that the dot product is kind of the projection of one vector onto another vector. Well, let's get to this thing, okay? And the Cauchy-Schwarz inequality, it's basically that the dot product of x and y will always be less than this quantity. All right, and it's this is equal only if x and y are parallel. Okay, so would equal this. Okay. Well, I'll leave it. Just look up. Cauchy-Schwarz inequality. Okay. I'll just mention it here, and then we can talk more about it later on. Okay. Then we'll talk about norms. Okay. Okay. So. Right. Okay. So a norm is a function and basically this is the symbol for the function that we're using. Okay, so it's a function from a vector space to the real number, set of real numbers. So we're taking a function, and when we apply it, we're applying it to a vector, and what the function outputs is a real number that satisfies the following. Okay, so if x is not the zero vector, then the norm of x must be greater than 0. Okay. And the norm of the zero vector must equal the number 0. The norm of ax must equal the absolute value of a times the norm of x, okay, for all a coming from a set of real numbers. Okay, and then we have what we call the triangle inequality, where the norm of x and y will always be less than the norms of their own. Okay. Okay, and so we've got a few examples of norms. I guess, and this is as far as we'll get today. Okay, so we have the L sub p norms, which is the norm of x, and then we often we might put a little p down there, and this is defined as you take each element within your x vector, raise it to the p power, and you add them up for all the elements in there, and then you take the pth root, okay, for p greater than or equal to 1, okay? And so we're probably, so the L2 norm, this is known as the probably the one that we're most common with, which is the Euclidean norm, which basically, so generally when you see a norm, they're talking about the Euclidean norm, but it's technically the L2 norm, and you take each element and you square it, and then you add them up, and then you take the square root of that, okay? And so if you want to say, what is the set of vectors where the Euclidean norm is 1, you'd get the unit circle, right? So this would be all the vectors where the Euclidean norm is equal to 1. All right. The L1 norm, this is called the Manhattan norm. Okay, and so in this case, basically you're just adding up the and you're not squaring it or taking the square root. You're just adding them up. Okay, and so basically, when you're looking at the set of norms here, it's not. It's that when you add them up, it has to add up to some distance 1. Okay, and so maybe if you go in one direction, you can get this far, and if you go in another direction, you can get this far. But you can imagine being in New York or in Manhattan, and you're traveling down the street, and you can't cut diagonally through the blocks, and so if you didn't go 1 mile completely in one direction, and you kind of made an angle, say right here, you would only get this far, right? You could go half a mile this way and half a mile that way, or something like that. And so the set of points where the L1 norm is equal to 1 gives us a diamond. Okay. So we are kind of just adding, that's the set of points there. Okay, so we got the L1 norm, the L2 norm, and then I guess you could have the L infinity. This would be the supremum norm, I think. And this is it's kind of the limit as you know, p goes to infinity of this exact thing. All right, and what does this norm look like? So if we're going to take the set where it's equal to 1, you're going to kind of get this this business where everything goes out to 1 here. Okay, and so you can imagine, because if you think of what goes on inside here, okay, so at any point less than 1, okay, you are taking it basically to the infinity power, and so this becomes practically 0, right? But then taking the, I guess the 1 over infinity, so it kind of forms this outside border perimeter there for the max norm or the supremum norm. Okay, we'll end there for today. We'll see you guys on Friday. Cover more of this matrix.
So I noticed this in the beginning. When you post your videos,